Hello, my name's Roger Watson and welcome to this session on principles of factor analysis. The session is going to deal exclusively with exploratory factor analysis, and in fact it's going to deal with mainly principal components analysis, which the purists will argue is not strictly speaking factor analysis, but it's very commonly applied, very commonly used, and gives you very similar results. The problem with factor analysis is it seems very difficult if you've not done it. It certainly isn't for the uninitiated. It does require high-powered statistical packages and takes a little bit of understanding, but there's no need to panic. No need to behave like this. In fact, don't panic. Factor analysis is a multivariate statistical method for reducing large numbers of variables to fewer underlying dimensions. Imagine coding a quantitative questionnaire for entry onto an SPSS database. Say you had 500 returns, you might code them from 001 up to 500. Then you might have a series of Likert type questionnaires coded, for example, from 5 to 1. You may have any number of these. So that's the coding, and that's what your database will look like on SPSS, or something like that. The problem is that there's absolutely nothing you can do by looking at those data, and it's very difficult to make sense of data like that if you don't reduce the data down in some way. Individual items are very little use if there are lots of them. Factor analysis falls within the range of methods that are used to establish validity. In fact, it's about factorial validity. And what factor analysis does is looks at different dimensions of a construct. For example, here we have service dimensions, and the dimensions thereof are quality of service, value for money, and expertise. That's an example of what factor analysis can do. If you asked a series of questions about service, you might find that they fall into different categories like that, and factor analysis would help to demonstrate that. That's an abstract example. This is the Edinburgh Feeding Evaluation and Dementia Scale, known as the EdFed scale. It's a 10-item scale concerned with the difficulties that older people with dementia face when feeding. And if we factor analyse this, we find a 2-item factor which is concerned with nursing interventions, a 2-item factor concerned with the observations that nurses make about feeding difficulty, and then a 6-item factor concerned with the behavioural aspects of feeding difficulty. There are different types of factor analysis. They are divided into exploratory and confirmatory factor analysis. Exploratory factor analysis includes methods like principal axis factoring, maximum likelihood factoring, and principal components analysis, although, as I've noted already, it's not strictly a form of exploratory factor analysis. And confirmatory factor analysis takes place only by structural equation modelling. I wouldn't worry too much about the distinction between principal components analysis and exploratory factor analysis, but it's here if you want to know it. It's easy to find on Google, and if you're very interested you can study it. Principal components analysis accounts for the maximum amount of variance in the observed variables, whereas exploratory factor analysis accounts for the common variance in the data. Principal components analysis looks at correlation matrices. Exploratory factor analysis uses adjusted correlation matrices. On the diagonals of a correlation matrix in a principal components analysis, everything correlates perfectly with everything else, and therefore the values are 1. The values on the diagonals in exploratory factor analysis are adjusted. Principal components analysis does other things too, which you can read there, but as I say, I wouldn't worry too much about this. So let's look at correlation and covariance, or in a sense correlation or covariance. They're very similar, they're related to one another, but they're not exactly the same. First of all, look at correlation. Principal components analysis analyzes correlation matrices of all the variables in the data set, and a correlation tells you how much variance in one variable is explained by the variance in another, for example variable x and variable y. We can think of them as being connected in some way, tied together. A correlation can be plotted like this. For example, we've got a blood pressure reading versus a stress test score, and the higher the stress test, the higher the blood pressure, and the line of best fit between those dots describes the correlation. And here's something else not to worry about too much, the equations for correlation and covariance. I think it's fair to say that these are the only equations you're going to see in the whole presentation. I've shown you these to show you how similar they are. The correlation is the covariance divided by the pooled standard deviations of the variables, and while factor analysis looks at a correlation matrix, what it's looking for is covariance between the items, the extent to which the items vary together. Factor analysis describes the variance in 3 or more variables, or strictly speaking, the covariance in 3 or more variables. We know how to look at the variance between 2 variables using correlation, for example variables a and b. If we introduce a third variable c, it immediately becomes very complicated, and you can imagine if you introduce more variables it becomes inordinately complicated. So the sources of variance in variables are common variance, specific variance, and error variance. Common variance is the variance shared between variables. Specific variance is the variance that is unique to a variable, and error variance is the rest, and essentially we can't minimize completely the error variance. So factor analysis is based on these assumptions. So the total variance of a variable is made up of the common, the specific, and the error variance. The specific and the error variance is unique to the variable, so that's called the unique variance, and the common variance and the specific variance is called the reliable variance. You don't need to know that, but the common variance is described as h squared. This is described as the communality, and the communality, it tells you how much common variance there is in each of the variables, and in other words how much variance is shared with the other variables in the data set. Here's another way of looking at it. You've got 3 variables, a, b and c. The common variance is all the variance that's shared between them in that central intersection and the 3 intersections around it. So what we're looking for in factor analysis is to see how much variance there is in common between the items. Conducting factor analysis, as I've already said, requires computer software. For exploratory factor analysis we can use SPSS, SAS and Stata, packages like that. For confirmatory factor analysis It's common to use AMOS, which is a bolt-on to SPSS and which reads SPSS files, so it's quite handy if you're using SPSS for your exploratory factor analysis. SAS and STATA run confirmatory factor analysis, and there's also highly specialised multivariate software like EQS and Lizral. And for both exploratory and confirmatory, the online public domain software called R can also be used. So now I'm going to look at the procedure for an exploratory factor analysis, and there's an excellent paper by Ferguson and Cox. It's given in the reading list at the end, and they really set the standard for carrying out exploratory factor analysis. They outline 3 stages. Stage 1, pre-analysis checks of the data. Stage 2, factor extraction, and Stage 3, factor rotation. So first let's look at Stage 1, the pre-analysis checks of the data. The assumption in a factor analysis is that the data are multivariate, that they're random, and that they're normally distributed. Clearly the data have to be multivariate, or you couldn't conduct a factor analysis. Quite often the data are not random, but in the ideal world they should be. And if you have a large data set of Likert type data, you can almost rest assured that it will be normally distributed. The tests of suitability for a factor analysis include the Kaiser-Meyer-Olkin test, the KMO test, and the Bartlett's test of sphericity. The KMO test is a test of common variance, and it tests to see that there is sufficient common variance in the data set to make a factor analysis worthwhile, and the value that you need here is greater than 0.5. On the other hand, the Bartlett's test of sphericity tests against an identity matrix. It's looking for the opposite to some extent. It's looking to make sure that the items are not identical, and that's estimated at a probability of less than 0.05. I have to say that in my experience with large data sets, I've never seen one yet that hasn't passed these tests of suitability. Before we move on to Stage 2, a word about sample size. It goes without saying that we need more respondents than variables, and the rule of thumb is 5 to 10 respondents per variable, and the minimum sample size is usually 100 to 200 respondents. You'll find different books on factor analysis giving you slightly different answers to this, and there are more sophisticated ways to work out sample size for the purists, and there have been some interesting papers recently on this. But if you follow these guidelines here, you're usually okay for a factor analysis. Normally in quantitative research we say that the bigger the better for sample size, but for factor analysis that isn't necessarily true. Large samples beyond the minimum requirements, and I'm referring here to exploratory factor analysis and not principal components analysis, can yield very trivial factors. So you need to go for a sample size that really meets your requirements and no more. So what does principal components analysis do? It uses a correlation matrix to search for covariance amongst items in the questionnaire. We've already covered the concepts of correlation and covariance. So it looks at a data set like this. Here you have the same items plotted along the top and along the side, and the correlations between them, and it's for a principal components analysis, so there's no adjustment to the matrix. All the items are perfectly correlated with one another. But just how do we do that? Well, as I've said, we need some high-powered statistical software. We'll come back to the actual procedure for running a factor analysis later. Now let's look at Stage 2, factor extraction. It may seem strange to be showing you a screenshot from SPSS here, which is one of the packages that we can use, but in actual fact you can use the default option, which is for eigenvalues over 1, which I'll explain in a minute, or you can actually set the number of factors that you suspect might be there. So that's one of the ways to do the factor analysis. You can actually set the number you want, or you can use the default settings which help you to make a decision, but I'll come back to that later. If you run a factor analysis, then what you get is the following. So if you run an initial factor analysis, then you get something called a component matrix, which is an unrotated matrix. We'll come to rotation later. Here you've got a series of subjects, school subjects or university subjects, English, French, history, maths, physics and chemistry, and then it's divided into two factors, either by default or because it's been set to show two factors. It doesn't really matter. You can get some idea that physics, maths and chemistry might be different from the other subjects because of the negative values under the first column. However, you have to be very careful interpreting negative values in factor analysis. It's the magnitude of the values that's important. The point here is that the magnitude of all these values is pretty much the same. It's very difficult to differentiate whether there is a difference between these two factors, and specifically it's very difficult to say precisely which items belong to which factors. You can hazard a guess, but this component matrix doesn't tell you that. You have to take further steps to see how many factors are present. Incidentally, under column 1, that's called the first principal unrotated component, and in reporting a factor analysis it's very important to report that. It's often missed out, but it's important to report that. This particular first principal unrotated component looks pretty good because all the values are roughly the same and quite large. If some values in the first principal unrotated component are very small, it can suggest that those items are not related to this particular set of items in this factor analysis, and you may need to think again. So how many factors are present? Well, this is what a factor analysis looks like when it's plotted out, and in fact you can't really tell there what's happening. You can't discern the factors at all. So you've got three items here in three dimensions: financial sector, retail sector and technology sector, and by looking at that it's difficult to tell. We have to undergo some further manipulations, essentially mathematical procedures, to clarify the situation. So we still need to decide how many factors are present. When you're running a principal components analysis, you normally just accept the default settings for a start, run the data, and then begin to make your mind up. But as you see, you can then actually set the analysis such that you choose a particular number of factors and go back and inspect them and see if the situation's improved. So deciding how many factors are present can be done using eigenvalues greater than 1, or the scree slope or parallel analysis. Eigenvalues are produced by a process called principal components analysis, and they represent the variance accounted for by each underlying factor. The problem with eigenvalues and using them alone is that they tend to overestimate the number of factors present and give you trivial factors. So this is part of the initial run of a factor analysis. It gives you the eigenvalues, the values on both sides, the initial eigenvalues and the extraction sum of square loadings are exactly the same. Don't worry about that. Look at the left on the initial eigenvalues. The value of the first eigenvalue is 3.029 and the next one is 1.291. This suggests that there are two factors present because those are both greater than 1. So that's quite clear. However, it's usual to augment the eigenvalues by using the scree slope method or some other method. The scree test was suggested by a man called Raymond Cattell. Here you plot the successive eigenvalues and look for a spot in the plot where the plot abruptly levels out. So the method is quite subjective, and Cattell named the test after the tapering scree at the bottom of a landslide on a mountain. However, the value of the scree slope test is that it tends to be more conservative in estimating the number of factors present than the eigenvalues greater than 1. Here's a scree plot, but you can immediately see the problem. Looking at this superficially, you might think, well, there are 2 factors there, a major one and all the rest, because if you draw a line joining those dots, it's roughly a straight line, but some people might say there are 1, 2, 3, 4, 5, 6 present, because the next break takes place at the 6th factor number. So it is subjective and some judgments required. Here it's a little bit more clear that there are 2, but some people might argue that there are 3, and here it's even more difficult to tell 3, 2 or 1. I would say 3, but other people might argue. So what I'm saying is that if you're using eigenvalues in the scree plot, they should be used together, and you can iterate to see what the best possible solution is. And often you learn what the best solution is by actually choosing that number of factors and running it and seeing if it makes sense, because ultimately a factor analysis has to make sense. You don't just rely on the mathematics to churn out a series of numbers. These days it's more common to use more sophisticated methods, and one of these is parallel analysis. This is a specific method for determining the number of components or factors to retain from a PCA, a principal components analysis, or a factor analysis, and it works by generating a random data set. You put in the number of variables and the number of people. It generates a data set that makes up a randomly generated data set and creates eigenvalues, and you compare the eigenvalues with your real data, and the ones that are bigger than your real data indicate the potential number of factors, suggesting that the other factors in your data may well just be what we call random noise. So it might be clearer if I show you how it works. So using a series of screenshots, I'll demonstrate, or I hope to demonstrate, how parallel analysis works. The software, the Monte Carlo PCA for parallel analysis, is in the public domain. You can download it. You can find it on Google. And you get 3 possibilities here: the number of variables which you know, the number of subjects which you know, and the number of replications to generate the random data set which you set. So let's imagine we've got 25 variables, 250 subjects, and we set the number of replications at 100. There's no real guidance on the number of replications you need to set. Sometimes 100, sometimes 250. It doesn't really seem to make much difference because I've run different data sets just to compare. Then you press calculate and it runs for a while. And then it runs and produces these random eigenvalues. I've enlarged it here to make it a bit more clear. There are 3 columns: the eigenvalue number, the random eigenvalue, and then the standard deviation, which we can ignore. There will be 25 eigenvalue numbers, and in your data set there will also be 25 eigenvalue numbers. What you do is you take your data set, the real data set where you've generated eigenvalues, and compare it with the random eigenvalues. For every eigenvalue in your data set that's bigger than the randomly generated eigenvalue, that suggests that that may be a real factor. So for example, if you had 3 eigenvalues, 1, 2 and 3 in your data set which were bigger than 1.622, 1.522 and 1.450 in this data set, but the next one was smaller than the eigenvalue in the 4th row there, then that would suggest that there are 3 factors in your data. Now we're still on stage 2, deciding on the number of factors. And now we've reached stage 3, which is the factor rotation. Factor rotation helps us to clarify the solution and see the putative factors more clearly than in the unrotated solution. However, which rotation do we use? The two rotations available, for example, in SPSS, are oblimin and varimax. Oblimin, which means oblique, assumes the factors are correlated. Varimax assumes that the factors are orthogonal, in other words, uncorrelated. There are different preferences in which you use. To be frank, the solutions often don't differ that much, but one may be a bit clearer than the other. This may be anathema to the purist in factor analysis, but I strongly advise running both to see what you get. But it's very unlikely that factors are not correlated. So I think if in doubt, and if you don't like my approach there, use the oblimin, because it's very unusual for factors to be truly orthogonal. So what we're trying to do with rotation is to gather together the items and show more clearly which covary, a little bit in this diagram here. So once we've rotated, this is an example here from a 4-factor solution, we get an output that looks like this. This is a 20-item questionnaire, C1 to C20. There are 4 components, or 4 factors here, and you can see that there are loadings there, as they're called. These are the correlations of the items with the factor. So how do we interpret a factor matrix? Well, we examine the loadings on the factors. As I said, these are the loadings, but what do we do with them? Select loadings greater than a particular value to indicate putative factors. But what should that value be? Usually it's 0.3 or 0.4, but it can be higher if you want it to be. Essentially, it's whatever helps you to interpret the factor matrix, but you must be consistent across the whole matrix. You can't use 0.3 for some, 0.4 for others, and so forth. You have to decide on a value and apply it. You can then choose another value, but it must be applied consistently across the whole matrix. And then you can see if you can see the solution clearly. So here you can see the loadings on the first factor. They're all greater than 0.4. They're indicated by arrows. It is possible, by the way, to ask for the output to gather the items together in their factors, but for clarity here and for the sake of this presentation, I'm not going to do that. I'm not going to indicate all the factors or it would get too messy, but for example factor 4 has got 3 items loading over 0.4, and you can see those indicated there. It's usual that the first component has the most items and the last component has the fewest. But what about instances where the item seems to load equally or highly on more than one component? There are other examples here. These are called cross-loadings. So what do we do with them? Well, they detract from the simple structure that we're looking at. A simple structure is one where the loadings on the putative factors are high, in other words, above the value of x, and those in the remainder are low, in other words, below the value of x. Cross-loadings should be removed. However, and this step is often omitted, the items that remain must be re-rotated and the solution inspected again. Finally, just a very quick word on exploratory versus confirmatory factor analysis, just for the sake of comparison and to introduce you to the idea of confirmatory factor analysis. First of all, is exploratory factor analysis adequate and or sufficient for the job? Well, it is, as it says, exploratory. You can't test a structure. You can only do that using confirmatory factor analysis. However, confirmatory factor analysis is very demanding in many ways on the data. It's very demanding in its criteria. It assumes an item loading of unity or 1 on putative factors and 0 loading of items on the non-putative factors. And we rarely have the opportunity to do it. It's very costly on data. You need large sample sizes. However, if you do run a confirmatory factor analysis using a package like Amos, the output looks like this. This is a 3-factor structure. The factors are all correlated, and what you see here is the correlation between the factors and then the loading on all of the items. And we can tell if a factor structure fits in confirmatory factor analysis by a series of fit indices, and you can see the sample size in the particular study I've shown there, over 3,000. There are various fit indices. Essentially they should all be over 0.9, and then the RMSEA, the root mean squared error of approximation, should be less than 0.06. In my view, exploratory factor analysis remains very valuable and even essential in establishing latent structures in large databases. Confirmatory factor analysis is an excellent tool if you have the luxury of multiple and large samples. Here are some useful references which are concerned with exploratory factor analysis, structural equation modelling, and with confirmatory factor analysis and integrated approaches. You might find it useful to check some of these references by yourself. Thanks for listening. This is my email if you have any comments or questions, and you can follow me on Twitter. Once again, thank you very much for listening.